Okay, next topic is P12, magnetism and the motor effect. Now, I taught you magnetism, but I definitely didn't teach the motor effect. I've done a tiny little bit of this with the morning intervention group from last half term. So I don't know whether we'll have completed this by the time you get to the mock, so I'm going to slow down on this now and just teach it. So it says sketch the magnetic fields around a pair of magnets in attraction. So that means we're going to need opposite poles. Ensure you label the poles of the magnet on your sketch. So I'm going to go north, south. Next to it, I'm going to have a magnet north, south. And I can see I've got opposite poles facing each other. Crucial part, in between these two, we'll end up with a uniform magnetic field. Don't draw too many lines. One at the top, one at the bottom, one in the middle. And we know magnetic field lines go north to south. So I've got a mark for that part there. Now I've got to draw all the other lines, and I've taught you butterfly, butterfly, straight, curve, curve. So I'm going to go butterfly, butterfly, straight, curve, curve. Make sure they're touching the magnet. Butterfly, butterfly, straight, curve, curve. Try to make sure they're not. So if that was the end of the magnet, straight, curve, curve, that is wrong. Okay, because all the magnetic fields from this area are coming out straight. And then north to south, out of the north, north to south, north to south, into the south, north to south. That's it, all drawn. Next one, what's the motor effect? So what this says is, if I've got a wire with electricity moving through it, or current, if I put a pair of magnets around it, it's going to move this wire. If this is 90 degrees, so imagine, let's draw that like that. There's my magnetic field north to south, if that's 90 degrees. If I was to put the wire parallel to it like this, it will not move. So the motor effect is this basic idea that if I pass electricity through a wire, so pass electricity through it, it makes circular magnetic fields. Now the spacing is telling you the strength. So it's strong near, and then it spreads out a lot because guess what? This is 1 over d squared. So if I was to draw another circle, I'm going to have it loads further away. But I've got these circular magnetic fields that are induced in the wire. And when I put a magnetic field around it, these interact. So that and that interact, and they're either going to force it up or force it down. And for that, we use Fleming's left-hand rule. And I will definitely teach that before the mock, because that isn't something you can just teach yourself, really, because it's quite tricky. So what is the motor effect? A current carrying wire placed perpendicular or 90 degrees to a magnetic field will experience a force. So how could you produce a uniform magnetic field in the laboratory? We've looked at it already. There's one. So you can see here the magnetic, so in, I'm going here and then not pointing at it, what a plonker. Here the magnetic fields are changing, but in there, wherever I am in there, the magnetic field's the same strength. This is a uniform magnetic field. So the best way to make a uniform magnetic field is just put a pair of magnets really close to each other. So put two oppositely charged plates close to each other, or magnets next to each other. Next one, which direction will the wire move due to the motor effect? So we're going to need Fleming's left-hand rule. You can see a dodgy experiment now, dodgy drawing. There's my first finger. There's my thumb. There's my middle finger sticking out. There's the other fingers. So that's my motion. That's my magnetic field. I'm going to put B. That's my current, I. And what I do now is I line my left hand up with this. So I'm going to point my first finger that way, north to south. I'm then going to have the current going up the page. I'm going to have to flip my hand over so that my current is going into the page. And I can see my thumb is pointing down when I do that. So this will move down. And I promise I will teach you that before the mock. How could the direction that the wire moves be reversed? At the moment that's going down, what could I do? I could flip these around, the north and the south pole, or rather than having the current go that way, I could do that. What I couldn't do is swap both at the same time. So if I did a north-south and swap the current, you happy? It'll then move down. So it's changed one of those. So reverse the polarity of either the current or the magnets, but not both. What will happen to the wire in this experiment? Well, we can see here's the magnetic field north to south. Currents going that way. They're parallel to each other. I'll teach you there are no physics gangster rappers in terms of this. So what will happen? The wire will not move because the current is parallel to the magnetic field. Okay, next one. We're then going to see we can do calculations on this, which is F equals BIL. So the force we experience is the magnetic field in Tesla times the current times the length of the wire in meters. So here we can see what's the magnetic flux. If the current is 2.4 amps, I'm happy with that, and the force is 0.06, I'm happy with that, and it gives me meters, no unit changes. So I want to work out B, the magnetic flux density in Tesla. So F equals BIL, rearrange it. B equals F divided by I times L. Shovel the numbers in. So the force is 0.06. The current is 2.4. And the length of the wire is 0.12. And that now gives me 0.21 Tesla. And that's that done.